So now I'd like to turn our attention to circuits that have inductors and capacitors in them, and then eventually we'll add EMF sources and resistors into the mix as well. But first, let's just start with a circuit that is simply an inductor in series with a capacitor. Now, if that's just sitting, if we don't do anything to get it into a state, it's just going to sit there. So let's just, we'll go ahead and somehow stick a charge of plus Q here. And a charge of minus Q here. I mean, we could maybe have Scotty beam it down there or something like that. For the moment, it's just a bit of a thought experiment. So what I would like you to do, though, is think about, pause the video and think about what the following sequence of events would look like. And after you've done that, let's get back here and debrief on that. Okay, so what's going to happen here? So initially, I'm going to have my inductor here, my capacitor here. Try that again. My capacitor here. I'm going to be needing this a lot, so let me copy it. All right. So initially, what I've got is positive charge here, negative charge there, and I'll have an electric field like so. The energy, there is no current initially. We just put charge here. It's just sitting there. So initially, all of the energy is going to be electric potential energy, and that will be proportional to the square of the charge. All right. Now remember, in addition to the electric field between the plates, there's also a fringe field coming off the plates like so, and they get realigned through the wires in the circuit. So we get a weak electric field running around like that. And what that's going to do is that's going to start peeling charges off of the plates. So let me just go ahead and drop in another one of these bad boys. All right, there we go. So in our next phase here, what will be happening is because of the fringe field, we will be driving an electric current through the circuit like so. Now the charges, what's going to provide the charges for that are the charges sitting on the plate. So that means that the electric field is going to be getting weaker, but because I'm pulling a current, that means that I'm going to build a magnetic field through the inductor. So if I think about my energy here, at this exact moment, the way I have it drawn, we'll have ourselves a 50-50 split of electric and of energy stored in the electric field and energy stored in the magnetic field. So that will be proportional to the square of the current. And this is proportional to the square of the charge, like before. So my charge decreased, my total electric potential energy goes down, and I'm building a magnetic field. So I'm taking energy out of the electric, as my electric field collapses, we're going to be driving a current that'll be making a magnetic field. So we're transferring energy from the electric field between the plates to the magnetic field in the solenoid. All right. In the next frame of our picture here, there we go. We'll go ahead and take a look at it at the moment when there are no charges on the on the capacitor. So there is no electric field holding charge. So that means that actually at this moment here, our current must be at a max. And this is because all of our energy is stored. All of our energy is stored in the magnetic field. So our charge went to 0, and our current is a max. Okay. And if we go take a look at the energy situation, our energy is entirely stored in the magnetic field. So, and since that's proportional to the square of the current, that has to be our max current. Now the thing is, we don't have any more electric field here to drive charges through the circuit. So this means that our current is going to start dropping, which means that our magnetic field is going to start collapsing. All right, so then in our next step here, there we go. We're still going to be having our current moving along like so. But now we're going to actually be shoving charges onto the plate. So, but here it's going to be positive charges on the bottom and negative on the top. So now our electric field will have reversed direction. Our magnetic field is, as we build up voltage here, as we build up charge here, our magnetic field, our current is dropping, and so our magnetic field is collapsing. So we'll have a weaker magnetic field again, still oriented the way it was before, like that. So now energy is coming out of the magnetic field because Faraday's law of induction says we're trying to keep the flux a constant but fail. That's inducing an EMF across the inductor, which is driving the current in the circuit. And now we're charging up the capacitor. All right, so in the next step, come on, there we go. So the next step here is going to be when we hit a max. So when we hit a max, our current is going to be 0. Our max of electric, max charge on the capacitor. And our electric field will be as strong as it can be. All right, but at the moment, we have no current. And now the process is going to start reversing itself. So in the next frame, there we go. Because remember, outside of the capacitor, there is a fringe field that ultimately will be redirected to follow the wires. We will be building up an electric field here, and that will start moving a current like this. So now we're flowing our current the opposite way. The charges that are getting shoved around are, oops, coming off of the capacitor. So as our current goes up, our charge on the capacitor is going down. So our electric potential energy will be decreasing. It means we'll be increasing our energy stored in the magnetic field. So now, because the current's flowing the other way, the orientation of the magnetic field will be reversed from what we had before. Okay, and we can keep this process going. As we go along here, so we will get to a point where our current has hit a max, which means that our capacitor plate will be fully discharged, and our magnetic field will be at maximum strength. And then our magnetic field will start to collapse. But that will induce an EMF that keeps shoving the charges along. There we go. So our collapsing magnetic field will continue to drive our current like so, which means that we will now start to put positive charges on the upper plate, negative charges on the lower plate, and start to build a magnetic field. And then the next step, well, that's actually oops, let's try that again. Our next step is actually where we started again. So I'm just going to say, and back to our starting point. So we start here, and then we end up back here, and this just keeps running forever. Now, a quick moment's thought on this. You might be asking yourself, is it really going to run forever? Pause the video and tell me what you think. Now, of course it can't. So that if it could run forever, that would be a perpetual motion machine of the second kind, one that violates merely the second law of thermodynamics, which is a machine that runs forever but doesn't do any useful work. So there has to be some way to lose energy out of this. So pause before you say that it's due to resistance in the wires, I'll just let you know that you can, with clever choice of materials, and if the materials are cold enough, you can have what's called a superconductor, which, due to quantum mechanical weirdnesses, the resistance in the wires is exactly zero. There is no resistance. Not almost zero, it is zero. So let's go ahead and assume we built this thing out of superconducting materials. We still have to have a way to lose energy out of the process. So brainstorm on how we might do that. Pause the video and get back with me. All right. Hopefully you recognized from earlier, I turned the drawing sideways to kind of hide what I was doing a little bit, and also just to fit everything in the screen better. Hopefully you recognize that this is Hertz's experiment. So the fact that I've got this continuously changing electric field in the capacitor, that's going to induce a continuously changing magnetic field, which induces a continuously changing electric field, which induces a continuously changing magnetic field, which means that we produce a transverse electromagnetic wave. So, real world, this thing won't run forever. It will lose energy by emitting radio waves. So what would the frequency of those radio waves be? Or for that matter, what is the frequency at which the charge is sloshing back and forth in the circuit? Well, remember from Eli the Iceman that the voltage and current are 90 degrees out of sync in inductors and capacitors, but in one case it leads, the other case it lags. So this means that the voltage at all times, whatever voltage gain you have in the inductor, you have to have a drop in the capacitor or vice versa in order to satisfy Kirchhoff's loop law. So this means that all times the voltages have to be the same, which means that we can demand that the EMF voltages be equal. So in this, so at resonance here, and this is a resonant circuit. We'll define that a little more later. The voltage across the RMS or max values of the voltage across the inductor and the capacitor have to be equal. By definition of reactance, this means that IXL has to equal IXC, and I can cancel the I's. So that means that the inductive and capacitive reactances have to be equal. So the inductive reactance is 2 pi FL. The capacitive reactance is 1 over 2 pi FC. What I'll do is I'll multiply through both sides by F, divide by everything that's non-F over here. You'll get that F squared is 1 over 2 pi squared LC, or taking the square root of both sides, the frequency is 1 over 2 pi root LC. So it turns out that what we have here is a simple harmonic oscillator. I argued that when we looked at Hertz's experiment earlier, and it oscillates at this frequency. So what can that get you? Now, if you remember from simple harmonic oscillators, they exhibit a phenomenon known as resonance, where if you drive an oscillator at the frequency it wants to oscillate at, you think about mass on a spring, and I keep tapping it at the frequency the mass on the spring wants to oscillate at, the oscillations get bigger and bigger and bigger. So with that, you can actually use something like you can use this idea to construct a radio receiver circuit. So for instance, let's say you're listening in on the FM band. Let's say you're tuning in to 88.7 megahertz, just to pick a station in the FM band. Now, you're going to build a tuning circuit based on one of these LC oscillators, just like Hertz did. A good typical value is something like 0.12 millihenries for these kind of tuning circuits. So what sort of capacitance would we need? Well, if we remember the frequency we want to get, it's going to be 1 over 2 pi root LC. Now we're trying to get C here. So with doing our algebra here, we can just square both sides. This will be 1 over 4. Let's see, 2 squared is 4, pi squared is pi squared, LC. And then I can cross multiply the F squared and the C to get that the necessary capacitance is 1 over 4 pi squared F squared L. Okay. So if we go ahead and put that in for this radio tuning circuit we're building, this is 1 over 4 pi squared 88.7 times 10 to the 6 hertz squared times 0.12 times 10 to the negative 3 henries. This will give you 2.68 times 10 to the negative 14 farads, or a couple hundred picofarads, which isn't an awful lot. So you might be wondering how reasonable that is, and the answer is, it turns out it's actually pretty reasonable. If you look in like some really old garage sale or something like that sometime, you might find a little transistor radio that you have a tuner where the tuner is to select the frequency instead of being something digital. It was actually just a dial with frequencies stamped on it, and you spin that dial around. Well, the way that thing worked is you would have a metal plate like so. You would have a sort of nut and bolt arrangement here that would go into the dial that you have there. Now, what you would do here is you would have a metal plate right here and a metal plate here, and you would have a film of plastic in between them, like so. And this is not a very impressive capacitor, but it doesn't need to be. We're not making very impressive capacitances. And you can adjust the capacitance, because when you turn the knob, you literally end up changing the thickness of the plastic as you move the little knob in and out, and that would adjust the capacitance to tune the station. So there you go. Alrighty, so for the last bit here, I'll present some results. For the most part, to properly derive the results, I would have to rely on resort to the methods of calculus. So here I'm going to present some results for RLC circuits and try to at least somewhat motivate where they're coming from. So I'm going to look at a series RLC circuit connected across an EMF source, and the order of the resistor, the capacitor, and the inductor don't matter. Like so. All right, so the key thing here is to remember that these voltages are both out of phase with the voltage across the resistor by 90 degrees. Now I'll say plus or minus 90 degrees because remember, Eli the Iceman, the voltage leads the current, and inductor lags the current in a capacitor. In a resistor, the voltage and current are always in phase, and this will always have a common current flowing through it. So it'll turn out that the applied EMF, I'm going to write it kind of weird here, the square of it, will be equal to, and these are RMS or max values, the square of the voltage across the capacitor plus the difference in the voltage across the inductor and, resistor, voltage of the difference in voltage between the inductor and the capacitor squared. So subtract and then square, don't square and then subtract. I can kind of justify this by saying, remember that sharing a common current, in the case of the resistor, the voltage would lead. In the case of the capacitor, the voltage would lag. And so this means that the voltage differences are working at cross purposes. Because there is a 90-degree difference with both of these, that should remind you of a right triangle. And so, yeah, this is actually coming from the Pythagorean theorem. That's as far as I'm going to motivate it here, but I just wanted to provide at least some sense for that. So I can go ahead and say that this is IR squared plus IXL minus IXC squared. And I can rearrange this to say that the current, again, RMS or peak doesn't matter as long as you do the corresponding thing, it'll be the EMF over the square root of R squared plus XL minus XC squared. And again, subtract and then square. This thing in the square root does get a name that you may run across. So this quantity in the square root will pick up the symbol capital Z and be called the impedance. And its units will also be ohms. So these are reactances. This is also an R-like quantity. These are reactances. They tell us how these devices react to the current. This tells us how the resistor resists the current. And so react and resist combined, I guess if you flip through the thesaurus enough, you decide that that must be impede. So that's where the word is coming from. So an application of this is actually with the electric company and how they bill, especially industrial customers. Factories, from an electrical perspective, are basically a giant motor. And with all those windings in the motors, basically the motors are giant inductors. So this means that a factory will have a fairly large inductive reactance. If there wasn't an offsetting capacitive reactance, that would mean that the for a given EMF, you wouldn't be able to deliver as much current down the transmission lines. That's not good for the utility, since they want to maximize how much they can deliver down the lines. So what they do is they actually set up they have a whole bunch of different incentives, but one of the things they do is they actually give billing incentives to factories to get the capacitive reactance of the factory to more or less match the inductive reactance. And so factories will have usually somewhere a room that's just chock-a-block full of really big capacitors, and that's just to try to get the inductive and capacitive reactances as close as possible to make the electric utility happy. All right, so we'll go and take a look just for a moment here as well. So if we take a look at our RLC, at these circuits here, we can plot the current as a function of frequency. So at the resonant frequency, which is 1 over 2 pi RLC, this is where you're going to have a maximum current as a function of frequency. And this will always be the case. Now, and if you go off resonance, this is where XL and XC aren't equal, and it'll fall off. It's not a Gaussian, but it's a kind of curve like that. Now, this would correspond to if our resistance was low. As our resistance goes up, the maximum current will drop. So this is in analogy to simple harmonic oscillators again. if you have low air resistance, let's say, the thing you can swing big amplitudes. And if you have high damping, high air resistance, for instance, it'll be lower amplitudes. And also, just to kind of cap off here, if we were to have, say, if we have an undriven circuit, so we'll say just a resistor, capacitor, inductor, and I give this some initial charge. We can go ahead and plot what the current would look like as a function of time. So we'll start off at some initial max value, and it will decay. And this is just like when we looked at damped simple harmonic oscillators before. So this would be, again, let's say this is a low resistance. And if the resistance is higher, it will decay more quickly. All right, so let's go ahead and let's say that I have a resonant circuit that wants to oscillate at 200 kilohertz, just to give this some concreteness. And let's say that I double the capacitance. What I would like to find is what is the new resonant frequency equal to. Well, something like this is an example of a scaling problem. And so we can remember that F0 is equal to 1 over 2 pi times the square root of LC. Whenever you have a scaling problem, what you can do is you can write like comma new and divide by the same expression, comma old. And as long as you divide by the matching things. Now you don't give the subscripts to things that don't change, so the inductor didn't change, but the capacitor did. There we go. So you can go ahead and cancel like crazy. Oops. And when you rationalize this out, you're going to get that this is the square root of C old over C new. So we can rearrange this. The resonant frequency new be equal to root C old over C new, F resonant frequency old. But they told us by saying we doubled the capacitance, we can write that C new is 2 C old. So I can cancel away here and be left with that this be the square root of 1/2 times our 200 kilohertz that we used to have. Well, that will now be 141 kilohertz. Alrighty, well, that will go ahead and do it for AC circuits. I will catch you on the flip side.